So let us discuss the second question of chapter 11, Dual Nature of Matter and Radiation of NCERT Physics of class 12th. And the question is that the work function of cesium metal is 2.14 electron volts. When light of frequency 6 into 10 to the power 14 Hz is incident on the metal surface, photoemission of electrons occurs. And it has been asked to find the maximum kinetic energy of the emitted electrons, the stopping potential, and the maximum speed of the emitted photoelectrons. So since the word photoelectrons, photoemission of electrons is being used, so it is pretty clear that this question belongs to photoelectric effect, which says that when light or any other electromagnetic radiation incident on the electron, primarily a cathode, electrons are emitted. These electrons are of variable kinetic energy, so they move from this electrode and eventually reaches to this electrode. So they establishes a connection, thereby closing this circuit, as a result of which a current is recorded in this microemitter. Now, as given in the question, the work function of cesium metal, let it be represented by phi to be 2.14 electron volts, and the frequency of the incident light represented by nu is taken as given as 6 into 10 to the power 14 Hertz. The first part of the question is to find the maximum kinetic energy of the emitted electrons. So this particular maximum kinetic energy can be determined from the Einstein's photoelectric equation, which says that maximum kinetic energy is equal to h nu minus phi, where h nu is the energy size of the photon associated with the incident light. H is the Planck's constant, and its value is 6.626 into 10 to the power minus 34 joule seconds, which is equal to 4.1357 into 10 to the power minus 15 electron volt seconds. Phi is the work function, which is given. Nu is the wavelength, frequency of the incident light, which is also given. So we can put the value of H and nu, H in electron volt seconds, nu in second inverse, Hertz is equivalent to second inverse. So if you put the value, these two terms, this term becomes 2.48 electron volts. This second and second inverse cancels. So we are left up with electron volts. We get 2.48 electron volts. When we subtract it with 2.14 electron volts, we get 0.34 electron volts. We know 1 electron volt is 1.6 into 10 to the power minus 19 joules. So if we multiply it with this factor, we get this value of maximum kinetic energy in terms of joules, which is 0.54 into 10 to the power minus 19 joules. Thus, the maximum kinetic energy of the emitted electrons is 0.34 electron volts, or 0.54 into 10 to the power minus 19 joules. This is the answer to part A. Now, as we know that when light is incident on the cathode surface, these photoelectrons are emitted, and they are emitted with different kinetic energies. It is due to the flow of these electrons from this electrode to this another electrode, which establishes a connection and forms a closed circuit, as a result of which current flows in the outer circuit. If you want that this current should come down to zero, we have to apply a negative potential to this electrode, relative to this electrode, with the help of a variable potential source. And the potential is being measured with a voltmeter. So eventually, if you keep on increasing this voltage, the potential difference across these two electrodes will change, which will generate an electric field. So this with respect to this potential source, this will behave as positive and this will behave as negative. So there will be an electric field in this direction. And this will impose a force on these electrons in the opposite direction. So if this is the direction of electric field, the force acting on the electrons will be in this direction. Simply saying that whatever potential we apply across these two electrons, as these two electrodes, the electrons in between them will experience a kinetic energy, will achieve a kinetic energy due to this, and which is equal to EV. Now, when this kinetic energy, when the current in this outer circuit becomes zero, it is only possible if no single electron can able to reach this electrode. So that is possible only if the maximum kinetic energy, the electron having the maximum kinetic energy is stopped by this potential, applied potential. So let us say we apply a potential V0 at which the energy experienced by the electron becomes equal to this maximum kinetic energy. Then even the electron with the maximum kinetic energy will stop and will not be able to reach this electrode. So we stop all the electrons, as a result of which there will be no current. This circuit breaks and there will be no current in this outer circuit. It is this potential V0 which is the stopping potential, and it has been asked to find out. So the relation is very simple. When this energy EV0 becomes equal to kinetic energy maximum, the potential corresponding to this, that is V0, is what is called the stopping potential. So V0 is kinetic energy maximum by E, which is 0.34 electron volts. So this E and E cancels. We are left up with 0.34 volts. So the stopping potential is 0.34 volts, not electron volts, volts. Thus, the stopping potential is 0.34 volts, and that is the answer to the part B of the question. In part C, it has been asked to find the maximum speed of the emitted photoelectrons. Obviously, it will be the speed of the photoelectrons having maximum kinetic energy. And we know kinetic energy max or kinetic energy is expressed as 1 by 2 mv square. So for the electrons having kinetic energy, maximum kinetic energy, this maximum speed would be V max. So this kinetic energy maximum can be expressed as 1 by 2 mv max square. So V max would be root over 2 times kinetic energy maximum by m. Kinetic energy maximum is 0.34 electron volts, and mass of the electron is 9.1 into 10 to the minus 31 kgs. We again implement the conversion factor of electron volts, that is the charge of the electron is 1.6 into 10 to the minus 19. So we are left up with, we do the calculation. So we get this V max to be equal to 3.46 into 10 to the minus 10 to the 5 meter per second. Thus, the maximum speed of the emitted photoelectrons is 3.46 into 10 to the power 5 meter per second. This is the answer to the part C. Thank you.